the maths with EJD. In this video, we'll be talking about branch and bound method for solving integer linear programming problem. Okay, the branch and bound, which you can call B and B, the branch and bound method is a general algorithm used to solve integer linear programming, that is ILP problems, where the decision variables are constrained. Decision variables are constrained to be integers. Okay. It systematically it explores systematically explores the solution space by dividing it into smaller subproblems, and that is so when you divide into smaller subproblems, that's where the branching comes in. And using bounds to eliminate subproblems that cannot lead to a better solution. That's where the bounding happens. Okay. The goal in the long run, the goal is to find, the goal is to find the optimal integer solution, the optimal integer solution to an optimization problem. Okay, so that takes us to the key steps in the branch and bound algorithm. Key steps in the branch and bound algorithm. Okay. The first step is initialization. Here, you start with an initial linear programming relaxation, of the ILP. So you have an integer linear programming problem, but then you relax it to a normal linear programming problem for easier solution, right? So start with an initial linear programming relaxation of the integer linear programming where the integer constraints are relaxed to allow to allow continuous variables. So first of all, forget about the integer constraint and get continuous solutions. Okay. So they are relaxed to allow continuous variables. Now, this provides an upper or lower bound for the optimal solution. So that's the initialization aspect. Let's talk about the next one, which is branching. So branching. So for branching, what you're doing here is to choose, you choose a variable with a fractional value. That is in the relaxed LP solution, in the relaxed linear programming solution. This is where you don't care about the integer constraints, first of all. So in the relaxed LP solution, and you create two new subproblems, create two new subproblems by branching. Okay. One of the subproblems, one where the variable is rounded down, is rounded down. Another one, it is rounded down or up, and one where the okay, I mean, let me just go one way to avoid confusion. One where the variable is rounded down, and one where the variable is rounded up. So this represent two subspaces of the original problem. So that is where branching is taking place. Then let's talk about the next part, which is bounding. It's branch and bound. So let's talk about bounding. So for bounding, right, you now here you solve the relaxed, linear programming problems for each subproblem. For each subproblem. So if the linear programming solution, is better than the current best solution, and the current best solution, okay, then you can update. So update the best solution. Update the best solution. But if the LP solution, is worse, if it's worse than the current best, then you discard it. You discard, or what we call prune it. You discard or prune it. So you discard or prune that sub problem. And then that leads us to the idea of pruning. Pruning. So initialization, branching, bounding, pruning is the next. So for pruning, right, if a subproblem, if a subproblem cannot lead, cannot lead to a better solution, e.g., if the solutions bound, if the solutions bound is worse than the best known, than the best known solution, then you discard it. You discard it and do not explore further. And do not explore further. Then that takes us to the last step where we talk about termination. So initialize, branch, bound, prune, and terminate. So that's termination as the last step in branch and bound. So the algorithm here, the algorithm terminates when all subproblems are either solved, where they're either solved or pruned. And the best solution and the best solution found is optimal. Okay. So initialize, branch bound, prune, and terminate. Now, having said all of this, can we take a problem to drive home the point? So let's take a problem to drive home all the points we've been making. So imagine this problem. Okay, let me just call it example. Let's call it this example. And here we need to maximize. We need to maximize z, which is 3x plus 2y, and that is subject to x plus 2y less than or equal to 5.5. And then we have 2x minus y is greater than or equal to 1. So those are the two constraints we have. And of course, we have x and y to be greater than or equal to 0. And at the same time, x and y are both integers. So this is where the integer programming thing comes in. So those x and y must be integers. We can't afford them to be non-integers. So, well, I think the first now you can solve this problem using any method you like. You can use a graphical method, you can use simplex method, but graphical method is easy, it's more straightforward, right? So we can go for that. So this is the problem we have, right? But before you can start okay, well, we can follow the steps, right? Just the steps we've listed now. So let's talk about step one, okay? Step one, step step one. That's where we talk about initialization. So that's the initialization stage, initialization. And that is where we talk about the relaxed LP solution, relaxed LP solution. Here, you ignore this part and then just solve it like a normal linear programming problem. Okay. So here, and that is going to, so here we're saying that initial, the initial linear programming relaxation is obtained by ignoring. So we ignore by ignoring the integer constraints. Okay, so we ignore the integer constraints. Now, from that, we are going to get a solution. So let's see what the possible solutions might be. So I'm just going to use graphical method. I'll just go straight to Desmos to get that, to get what the possible solution might be. All right. So, of course, we already know it's about the four corners. So what are the constraints? We have x plus 2y less than or equal to 5.5. So we have that red region or something like that. Then we now have 2x minus y greater than or equal to 1. So we have that region also. So you see, this region is where the two overlap. So we need this corner. So this corner is 1.5 and 2. This corner is 0.5 and 0. And this corner is 5.5 and 0. So 1.5 comma 2. Okay, I guess I want to note that somewhere 1.5 comma 2. That's what we should have done, right? If we're going to use the graphical method. So those corners where solutions may lie there. So we have 0.5 comma 0. We have 1.5 comma 2, and then we have 5.5 comma 0. So those are the corners that are most likely going to give us the maximum solution. So with those values now, I go back and try to find which of them might be optimal. Okay. So, um, okay, I can say using the graphical method, using the graphical method, the corners of the feasible region. The feasible region is where the blue and red overlap. So the corners of the feasible region are, so if you like, you can say A is 0.5 comma 0, B is 1.5 comma 2, and C is 5.5 comma 0. So these are the corners. So one of these would give, we are maximizing. So we have to bring in the objective function. So we can have the objective function is Z, which is 2x plus 3y. I mean, 3x plus 2y rather. 3x plus 2y. So we need Z of A. So ZA would be 3, or rather that would be Z evaluated at 0.5 comma 0, and that would be 3 times 0.5 plus 2 times 0, and that is 1.5 plus 0, and that is just 1.5. So that is ZA. And we can do ZB. ZB is Z evaluated at 1.5 comma 2. So that is 3 times 1.5, right? 3 times 1.5 plus 2 times 2. So that is 3 times 1.5 is 4.5. 2 times 2 is 4. So we have 8.5. Okay. And lastly, we have ZC. ZC is Z evaluated at 5.5 comma 0. Okay. So that is 3 times 5.5 plus 2 times 0. So that is 3 times 5 is 15 plus 3 times 0.5, that is 1.5. So everything is 16.5. So you can see from everything now that, okay, we have, this is the biggest, 16.5 is the biggest. So we see this, okay? So we can say, so the optimal solution here, solution, the optimal solution is x equals 5.5, y equals 0, and z equals 16.5. So that's the optimal solution. And that is the first step. So when you initialize, that's the first thing you get. So the next thing we want to do is to go branching and bounding. Okay. So now the reason for the branching is because you can see so what we have got here, we have x we have x to be 5.5. Y is 0, so we may not have to worry about that. But we have to branch on 5.5. So that takes us to step 2. So step 2 now, where we have branching, okay? We have the branching. And since we are looking for an integer solution, right? So we branch on x since it has a fractional value. Since it has a fractional value. Okay. So this creates two subproblems. This creates two subproblems. This creates two subproblems. So subproblem one, subproblem one would be, since y itself, right? Um, you know, x rather, x is 5.5. And what we said under branching is that, so if you round this down, okay, if you round this down, it goes to 5. If you round this up, it goes to 6, right? So the first sub problem, you are going to take that to be the rounded down part. So the first sub problem is going to be um x less than or equal to 5. That's the first sub problem. And the second sub problem, that's sub problem 2, sub problem 2 would be that would be x greater than or equal to the rounded up part. Okay, so you have 5.5. So you go down and you have x less than or equal to 5. You go up and you have x greater than or equal to 6. So those are the two sub problems now. So you now solve these ones in turn. That's where the whole branching thing takes place. So if you go for sub problem 1 now, sub problem 1, where you have x less than or equal to 5. So what you're now going to do is you now try this out on the constraints. So you have the the constraints of the subproblem, the constraints of the subproblem are, so the original constraints you had in the original problem, right? So x plus 2y less than or equal to 5, 2x minus 1 is greater than or equal to 1, all those things you have. So that's x plus 2y less than or equal to 5.5, 2x minus y greater than or equal to 1. So now, since you're solving subproblem 1, so you have an additional constraint, that is x is less than or equal to 5. And then you have your normal xy greater than or equal to 0. But no, now we are focusing on integer programming, right? So um if you solving the relaxed LP. So you now relax the LP again. Relaxed LP for x equals 5. Okay. I mean, we can easily do this without even having to go to the graph. So you see, step 1, from x plus 2y less than or equal to 5.5, right? Okay. So we already have, so since we are relaxing it, it means we are saying instead of the x less than or equal to 5, we're just saying x is equal to 5. That's what relaxation is about. So from x plus 2y less than or equal to 5.5, right? It means that we are going to have x is now 5. Okay. So we have 5 plus 2y less than or equal to 5.5. So that implies that 2y is less than or equal to 5.5 minus 5, okay? That's you transferring this down here. So 2y now is less than or equal to 0 0.5, right? That's 0 0.5. So y now is less than or equal to 0 0.5 divided by 2. So y is less than or equal to 0 0.25. Okay? Y is less than 0 0.25. So since y is less than 0.25, we need an integer. So the best answer here. So this will simply mean that y is equal to 0 because y has to be less than 0.25. 0.5 is not an integer. So the best of this we can take is the fact that y is equal to 0. Okay. So in that case now we have we have, so it means the solution in that case That's at least for the first part, right? The solution here is x is 5, right? Then y is 0. That's what we have from that place. Okay. Then if we take that into the objective function, so we now say z evaluated as at 5 comma 0, z evaluated at 5 comma 0 is equal to what's the z again? 2 z is, I think we just did something with that. Okay, 3x plus 2y. So that is 3, 5 plus 2. So don't forget z is 3x plus 2y. So that means 3, 5 times 2, 0. Okay, and that gives us 15. That gives 15. So you keep the 15, right? Because we don't know what the next one is going to give us. But we have only done one part of this, right? So this is one constraint. Okay. Then um okay. Then probably before I even come here, right? Before I come to this, let's leave this first. Let's do the two parts. We have to do the two constraints together before we conclude. So let's do the two constraints. So for the second constraint, right? For the constraint 2, that's2x from 2x minus y greater than or equal to 1. So here, of course, x is 5, so we have 2 times 5 minus y is greater than or equal to 1. So this implies that 10 minus y is greater than or equal to 1. So that means that 10 minus 1 is greater than or equal to y, right? So that tells us that 9 is greater than or equal to y, which means that y is less than or equal to 9, okay? Y is less than or equal to 9. Well, I guess we shouldn't even worry about this first, okay? Because we have to look at everything all together. We have to consider everything together. So here, y, we have y to be less than or equal to 0.5, and here y is less than or equal to 9. Okay. And what we can take from that is that, of course, we know y is greater than or equal to 0, right? And if y is going to be less than or equal to 9, the feasible range for y is, okay, here we have y, what is happening here? Y is less than or equal to 9, right? So y is less than 0.25. So the stronger thing here, right? Now, if we look at, okay, I mean, if we look at the number line, so y is both less than 0.25. Um, let me do this. Y is less than equal to 0.25 and y is less than or equal to 9. So the stronger one here, so if you look at that now, so the stronger thing is that y is less than or equal to y is less than or equal to 0.25 is stronger, right? Stronger than y less than or equal to 9. So in that case, the best we can have, y is less than or equal to 0.25 simply implies that y is equal to 0. And from that now, the solution overall the solution overall will be 5 comma 0 from that from subproblem 1. So in that case now, from z equals 3x plus 2y, so we have z evaluated at 5 comma 0. That will be 3 times 5 plus 2 times 0, and that is 15 plus 0, and that is 15. So that's what we have for subproblem 1. Okay, that's what we have for subproblem 1. So let's go for subproblem 2 and see if that also works any magic. So here, don't forget, we have x is 5, y is 0, whereas z is 15. So that is the optimal solution we have from subproblem 1. But we also have to do, we have to solve problems. Let's do solve problem 2 to see if we are going to get a better result from that. Okay. So that takes us to sub problem 2. Say sub problem 2, where x is greater than or equal to 6. X is greater than or equal to 6. And what we are going to do there again is that we have the constraints. The constraint for this sub problem will be the original constraints we have from the beginning. Those are x plus 2y less than or equal to 5.5, and then 2x minus y greater than or equal to 1. Then in addition, now we have x greater than or equal to 6, and then we have x comma y is greater than or equal to 0. Then we have to relax it again, right? To find the solution, of the relaxed LP problem, okay? Again, we set x to be 6 because this is the key thing here now. We set x to be 6. And if we set x to be 6, we take the constraints, these two constraints, one after the other. So we now say from x plus 2y, less than or equal to 5.5. So we have this one now is 6 plus 2y less than or equal to 5.5. Okay. In this case, that means we have 2y less than or equal to 5.5 minus 6.0. So 2y is less than or equal to minus 0.5. So that means that y is less than or equal to minus 0.5 divided by 2. That means y is less than or equal to minus 0.25. Now, y cannot be negative. The worst y can be is 0, okay? So this leads, so you can see that this actually leads, to a contradiction. This leads to a contradiction, okay? Because uh y is always greater than or equal to 0. Y has to be greater than or equal to 0. So it can't go negative. Talk less of being less than minus 0.25. So in that case now, that already destroys the argument. So we can say therefore the sub problem 2 is infeasible. Okay, the sub problem 2 is infeasible and can be discarded. Okay, doesn't give us any hope and can be discarded. So we don't even have to worry about the other constraint. For the other constraint, right? If we're going to try that, so you'll be having 2x minus y greater than or equal to 1. So you have 2 times 6 minus y greater than or equal to 1. So that is 12 minus y greater than or equal to 1. So that means that 12 minus 1 is greater than or equal to y. So 11 is greater than or equal to y. That means that y is less than or equal to 11. But in the case of less than, right, the smaller one takes the cake. So you have y is less than or equal to 11, and then you have y is less than or equal to minus 0.25. But because this is smaller, right, it will supersede this, just like 0.25 superseded 9. So, and since this cannot be fulfilled, then it breaks down the whole thing. So the sub problem 2 is infeasible and can be discarded. And that takes us to step 3. Step 3, that is where we do our pruning. And probably, of course, if we have more situations, we can still keep going. So that leads to our pruning, right? So we say since sub problem 2 is infeasible, it is pruned. It is pruned. Okay. Then we can now go to step 4. Step 4, that's where we have termination. Okay, I mean, what is even actually happening in step 3 is more like where we are doing the uh, branching and bounding. So I think it's more appropriate to call this branching and bounding. Okay. After the branching and bounding, we have the pruning. We have the pruning in step 3, and then step 4 is the termination. So since we are going to discard subproblem 2, then we just agree that um, the optimal integer solution, the optimal integer solution is from is from subproblem 1. It's from subproblem 1. Okay, the optimal integer solution is from subproblem 1, and it is x equals 5, y equals 0, and z equals 15. Okay, so we can say therefore, therefore, the optimal solution, therefore the optimal solution to the given integer linear programming problem is the same. X equals 5, y is 0, and z is 15. So this solution is the best, this solution is the best integer solution. Of course, we have a better solution if we don't care about integer, which is 16.5. But since we need integer, right? This solution is the best integer solution. All right. Um, as the relaxed, as a relaxed linear programming solution had an objective value of 16.5, which is which is higher, which is which is higher, which is higher than 15. But the fractional value, but the fractional, x was 5.5, but the fractional value of x being 5.5, right, in the relaxed linear programming, programming precluded a valid integer solution. Okay. So in that case now we can say thus the branch and bound method, the branch and bound method has successfully determined the optimal integer solution, to be um x equals 5, y equals 0. I mean, this feels like a broken record, but I mean, it is what it is, like they say. So that's what we have. So we need to state all the premises. All right, so as far as branch and bound is concerned, that is how it's been today. If you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. And don't forget to comment. Let me know if there's a topic you like me to teach or a problem you like me to solve. And of course, like and share so that more people can have access to all this great content. In the next video, I'll be showing you the Python code for this. But that always makes things faster and easier. So till then, have a nice time. Bye.